Hi, my name is Preston Ward, and today I'm going to be talking about imposter syndrome, classifying salamanders with computer vision and artificial neural networks. And so before we begin, look at these 4 salamanders and try to remember which species they belong to. There's 4 salamanders here and 4 species, and we'll come back at the end and see how you did. And so why would we want to study salamanders? And so this group of salamanders are incredibly interesting because while genetically speaking, they are wildly different, you can't distinguish them by sight. And so they can provide good insights into models for evolution and behavior. The reason that we can't do this yet is because it's just too expensive. The cost to get started is anywhere from $80,000 to $695,000, let alone paying people who can do the analysis, and each sample can cost up to hundreds of dollars. So the way we decided to try to look at this is by using neural networks. And so without getting too into the weeds, neural networks consist of nodes or neurons connected fully from one layer to the next, where each neuron is weighted, and through a training process, those edge weights get adjusted. Over time, it will learn to recognize patterns, and all of these black dots over here on the left represent inputs, which usually be like a row in an Excel spreadsheet. And the dots over here represent the outputs. And so in our case, these would be the salamander classifications. The specific time we're using is called a convolutional neural network. And so what we do is we take a mathematical convolution and then feed that into the fully connected layer. And all that is a way to get features out of an image. And the way that works is we take an image, and so that's represented by the matrix in the back here. And then we move over it with another matrix called the kernel. And this is going to describe some function of how they got applied to each other. And that is going to produce our new image. And this is the convolutional step. And we might do multiple of these because it helps reduce dimensionality, and it pulls out the most important features that we're looking at. So we get the benefit of reduced size with the same amount of differentiation in the features of the image. And so here's the final network that came out. We won't get into this here, but if you're interested, please tell me. And the data and how we did. So all images were provided by George Washington University and the Smithsonian. We had 297 photos in 4 unique classes after implementing a filtering and image standardization process. These were broken into train and test sets of 235 and 59 images, respectively. So here's our original salamanders. I bet you can probably tell some of them apart, and that's called overfitting. You found small features inside the salamanders and focused on those, and we don't want our networks to do that. So we'll introduce one more of each species. Can you tell which of these the classes belong to? And I'm willing to bet probably not. And so our network also had to deal with this. So how did it do? Well, we were actually able to achieve an accuracy of about 79%. And we feel that's awesome given our small sample size, and we really want to get more images so that we can push this farther. And we were pretty thrilled with that. So our future work, we'd really like to see what these neurons are firing on, essentially. What is getting them excited? Is it just the difference in size between the salamanders is how we can tell them apart? Or is there patterns on the back that we just can't notice yet? So we'd like to see that. Big thank you to everyone who's helped on this project, and thank you for watching this. And yeah, goodbye.